Okay, guys, can you see that okay?
Yep.
Perfect. All right. So I might just go through one of each, okay? Just so we're not here all night kind of going over the same question. But just before we get started, how did you guys get on with the questions? Did you find them okay? Or was there any you got stuck on in particular that I could focus on now? So I suppose out of all of them, is there anything in particular you'd like me to focus on? Or we just go with all of them? All of them. Okay, fair enough. Yeah, so I suppose I'll get started at the beginning then. So I'll take one of these examples. All right. So it's these are just simple kind of molecular weight calculations. Okay, so I covered these in the face-to-face lecture that we did last week, but I'll go through one of them now. Okay, so I'm going to take question two there. Okay, so this is calculating the molecular weight of calcium carbonate. All right. With any of these, what I recommend you do is write down all of the elements one after the other. Okay, so in this case, we have calcium, we have carbon, and we have oxygen. Okay, so I'd write those down in the list on the side for yourselves. For each one, then we can take the molecular weight from the periodic table. All right, so I'm taking these directly from the periodic table itself. So calcium does not have a weight of, just bear with me 2 seconds. Okay, so again, taking this directly from the periodic table, calcium has a mass of 40 grams per mole. Carbon then has a mass of 12 grams per mole. And oxygen then has 16 grams per mole of a mass. So then what you do is you multiply them by the number of atoms of that element you have in the molecular formula. So in this case, I only have one calcium, so I'm just going to multiply it by 1 there, but you don't have to do that normally. For carbon, it's the very same then, so I'm going to multiply it by 1 just to show you where that comes from. And then our oxygen, then we have 3 oxygen atoms there, so I'm going to multiply that by 3. Is everyone okay so far? Everyone can see where I'm getting that?
Yeah.
Okay. So of course that will equal 40 grams per mole in total for my calcium, 12 grams per mole for my carbon, and then 16 by 3 is 48 grams in total for my oxygen. So to get the total molecular weight there, all you have to do is add each one of these together. Okay? So for this particular example, it will be 40 plus 12 plus 48. Yeah, and that will give us actually 100 grams per mole as our molecular weight for that. Okay, so that's our total molecular weight for our compound there, calcium carbonate. Is there any part of that, guys, you want me to go back over? Okay, so you'd approach each one of these in the exact same way. So I might do this one just to show you how the brackets work. But again, it's the exact same format, all right? So I might just copy and paste this down here. And I'm going to do part 3 there just to show you the kind of difference in the brackets, all right? But it's done the exact same way. Okay, so in this case, then we have calcium, we have a phosphorus element in there, and we also have oxygen. Okay, so it's Ca, P, and our O for oxygen there. Our calcium there, so it's still 40 grams per mole, but in this case, I have, and I'll zoom in a little bit so you can see it there. Okay, so I have 3 calcium atoms. All right, so I need to multiply that 40 by 3 for this example to give me 120 grams per mole. All right. The way the bracket works is that this bracket here represents a group. Okay. Any subscript you see outside of a bracket means that in this case, there's 2 groups. So this is almost a group in itself, and this subscript represents that we have 2 of those groups. Okay. So in the molecule in total, we have 2 of those groups. So we need to show that we have 2 phosphorus atoms there. So that would be 2. Now I just need to double check the molecular weight of phosphorus. So yeah, so that's 31 there. Okay, so again, anything in the bracket represents a group on that molecule. We have two of those groups, so we need to represent that we have two of each of those. Okay. For your oxygens then, so on that group, in this kind of subgroup, we'll call it, there's 4 oxygen atoms. Okay. But in total, we have 4 oxygen atoms on one group, 4 oxygen atoms on the other. So we have 8 in total. So it's 4 by 2. Okay, so we need to multiply that by 8 there. So anything you see outside of the bracket, you basically multiply in, okay, because it's representing that we have a certain number of groups of each one of these. Is everyone okay with that so far? Yeah? Everyone can see where I'm getting those values from.
Yeah.
Perfect. Okay, so in that case then, sorry, I'll come back up here. So that's going to be 62 grams per mole for that. 16 by 8 then is 128 grams in total. So to get the total molar mass of what I have, I just need to add each of these three numbers together. So that's 120 plus 62 plus 128. So in this case, it will give me a total of 310 grams per mole for Ca3PO42. Is that okay, guys? Everyone happy enough with that?
Yep. Yeah.
Yeah.
So sorry, just to clarify. So when you have that bracket there and the two outside just means double what's in the bracket.
Exactly, yeah.
Yeah.
So if I just remove that two there,
Yeah.
that represents I only have one
One.
kind of phosphorus
Okay.
group.
Okay.
Once that two goes in, I have two groups, so that's when I need to represent them both.
Okay. Perfect. Thanks.
Similarly, then, just to point it out, if that was a 3 or a 4, you'd multiply everything in the back by that number.
Okay. Yeah. Thank you.
Perfect, guys. So what I'll do is I'll move on then to our percentage composition. Okay, so I've done kind of one example out, but I'll talk through that one here. So this is part 4 of that, okay? So cypermethrin, okay, is a synthetic insecticide and has the chemical formula as we can see here. So this question asks us to find the percentage composition by mass of just carbon. Okay, so these are kind of set exam questions, so they'll kind of give you a little bit of a spiel about the compound itself. But all you need to know here is that, and the important parts are the compound you're working with, and then if it tells you specifically what element we're looking for. Okay, so in this case, it's carbon. Because what they can do is it's almost not to confuse you, but they'll add almost like a paragraph of information about what you're looking for. But it's important to point out or highlight the important parts of that. Okay, so most of the time it's going to be a mass or your chemical formula, and then what element we're actually looking for here. Okay. So in any of these types of calculations, what I recommend you do first, oh, sorry, go back up to the top here. So your first step in any of these calculations should be calculating the formula weight or the molecular mass. Okay, so that's exactly what I've done in the first. Sorry, I'll scroll down. Exactly what I've done in the first couple of questions that I've done. Okay, so it's just calculating the molecular weight. So if I see here, I'm just going to copy this down so we can see it. So I'm getting the formula mass of my compound there. So in the exact same way what I've done, okay, so I have carbon, I have hydrogen, chlorine, nitrogen, and oxygen. And for each one of them, then I take the molecular weight from the periodic table and multiply it by the amount of those atoms that I have. All right. So in this example there, so there's 12 grams per mole multiplied by 22 for my carbon, 1 gram per mole multiplied by 19 for my hydrogen, 35.5 multiplied by 2 for my chlorine there, nitrogen 14 grams per mole by 1, and oxygen then is 16 grams per mole by 3. So all you do is add all the total of that up, and that will give you 416 grams per mole for that particular compound. Okay. So what I recommend you do, guys, even for the exam, if you can't get to the percentage composition, or in some of the later questions where you have to convert mass to moles or moles to mass, Even if you can't get that far, what I do is I would do this step. Okay, because that's going to be relevant to every single question. But you will get attempt marks for calculating the molar mass. Okay, so even if you're completely lost, can't figure out the conversion from mass to moles or vice versa, I would recommend just doing that. And even if you left it at that, that's fine. Okay. So moving on then, so that I've taken this directly from our slides. Okay, so to work out the percentage composition of any element within a formula, you take the atomic mass of that element we're looking for, multiply it by the number of atoms of that element that are in the formula, and then put it over the total formula weight of that compound. Okay. So in this case, it asks for carbon. Okay, so it's our carbon 22 there. So all I have to do here was take, now you can do this out and have a figure for that there, but I've just done it out like this. Okay, so it's 12 grams per mole for carbon from the periodic table of elements. Multiply it by 22 because I have 22 carbon atoms in this whole formula. And then I've just calculated my formula weight as 416 grams per mole. Okay, so I input all that into this equation here, and it should give me a final answer of 63.46%. Okay, so similarly, just to show, now I know the question didn't ask this, but I'll just show you a second. Oh, sorry. I'll show you a second element there. Okay. So for example, if we were asked for chlorine in this case, all we would have to do is take, and it's kind of a common enough exam question that they'll ask you for one and then ask you to repeat that with another element. Okay. So if we were asked for chlorine in this case, you take the atomic mass of chlorine from the periodic table, 35.5. We have two atoms of chlorine, so we'll take that into account. And then we still divide it by the same total formula weight, okay? Because it's the same compound, it's just a different element. So in that case, it'll be 35.5 multiplied by 2 and then divided by 416. So in this case, then it will be 17.07% if it was chlorine. Okay, so you can do this for each one of those, and some questions do ask you for that. They'll do each element. Some will only specify what element they want, but it's good practice to work through them all. So if that was the case, that would be for chlorine. Which makes sense, okay, because if you look at the percentage composition, we have the most carbon atoms in this formula. So that should take up a significant amount of the composition, which it does, around 64%. Chlorine, even though it's a heavier element, there's only two atoms, so it should take up far less of the composition than, say, carbon or maybe our oxygen or our hydrogen there. Is that okay, guys? Does anyone have any questions on that so far? Okay, perfect. Okay, so I'll do one of the balancing chemical equations questions there. So I have one done out, so I might just take this one and start again. Okay, so I'm going to do part B there. Okay, so a common enough exam question here would be you'll get a balanced chemical equation, or sorry, an unbalanced chemical equation. Your first part of the question will be to balance the chemical equation, and then typically using the balanced chemical equation, it'll be to work out the mass of either a product or reactant, and then take it one step further then into conversion in moles using the molar mass. Okay, so these kind of tend to make up the same question over and over. So what I recommend you do, so I would write each of your elements down on the left, okay, almost like in a table. So in this case, I have hydrogen, I have a sulfur there, I have oxygen, and I have sodium. Okay, so I have my hydrogen there, sulfur there, oxygen here and here, and then my sodium. Okay, so any element that you have on the left-hand side, you list in a table. Okay, because they should be on the other side as well, okay? Because conservation of mass, we're not making any new elements here, we're just converting them from one form to another. So your first step there is just to count what you have on each side. Okay, so for hydrogen, for example, in total on the left-hand side, I have two hydrogen atoms there, one hydrogen atom there. So I have not 32, three in total. Okay. On the right-hand side, then I only have two. Okay, so just my H2 there. Sulfur then, so I have one on the left-hand side, just in my H2SO4 there. And it looks like I only have one on my right-hand side as well. Oxygen then, so I have four in my H2SO4 and one in sodium hydroxide, so that will be five in total. And then on the left-hand side, I also have, yeah, I have five there as well. Okay, so four oxygens there, one for my water, so five in total. Sodium then, by the looks of it, I just have one on the left and then two on the right. Can everyone see where I'm getting those from, yeah? Okay, so this is why I recommended doing it this way because you can easily see what has to be balanced and what doesn't, and it's quite easy then to cross off as you're going through. Okay, so what I recommend you do is take each element one by one. So in this case, I might leave this one till last because it's a little bit more awkward, and I might be able to balance it based on what I do next. Okay, so if there's any ones that are kind of a not, I suppose, see sodium there. I can easily balance that by putting a two on the left. So what I recommend you do is don't start with any ones that look a little bit awkward, okay? They have three on the left and two on the right. So in that case, I'm going to start with sodium because to balance that, all I have to do is put a two on the left-hand side as such, okay? So there. By doing that then, so I would recommend crossing it off and then writing what you put in next. So I put a two on that side and now my sodiums are balanced. Okay, so I have two sodium atoms on the left, two on the right. They're now balanced. What I have to make sure now is that anything I did to the other elements in that compound, it's reflected in my table as well. Okay, so by doing that, you see now that I now have two oxygens here, plus four from my H2SO4. So now I don't have five anymore, I have six. Okay. Similarly then for my hydrogen atoms, so by putting the two there, I've essentially created two hydrogen atoms for my sodium hydroxide, plus two. So that's no longer three. That's now four. Can everyone see where I got that from, yeah? All good so far? Okay,
Yeah.
so by putting that there, I've essentially changed not only the sodium, but I've also changed the number of oxygens and the number of hydrogens in this compound. So I need to take that into account now. And by looking at this, I've now unbalanced my hydrogens and my oxygens. Okay, so now I need to look and see what I have to do for these now. So in this case, okay, so looking at my hydrogen next, because that's almost like a simple 4:2. If I put a 2 on my right hand side to bring this up to 4, that should balance. Okay, so I'll show you what I did there. So now on my right hand side, I no longer have 2, I have 4. Okay, because my 2 multiplies in, so that's now 2 by 2 is 4. I have 4 on my left hand side, so now my hydrogens are considered balanced. Is everyone okay with that so far, yeah? So now I need to look and see how that affected the other element in my compound, okay, which is oxygen. So I now have two oxygens, okay, so 2 by 1 is going to give me 2 plus my 4 on my sodium sulfate. So by doing that, I no longer have 5 on this side. I have 6. And now my oxygens are balanced as well. Okay, so by adding a 2 in front of the sodium hydroxide, 2 in front of my water, I've essentially balanced all of the elements. But this is why I recommend doing it in a table like this, because you can physically tick them off as you're going. You can cross them out, and then it's easy to see which ones you have to balance next. Because it can get very, very confusing if you're trying to balance them all at once and you're not sure how it's affecting each of the compounds individually. Okay? So what I recommend you do is in an exam, create a little table like this for yourselves, list every element on the side, your initial numbers on each side, and then take it one by one then. Is that okay, guys? Okay, perfect. Okay, so I'll move on then to, sorry, now I'm just working my way through the questions here. So we might do an empirical formula question if that's okay. Everyone happy enough to do that? Okay, so I'm going to do part 2 there. Okay. So just as a recap from last week, okay, so your empirical formula is the simplest ratio of the moles of each of your elements together, okay? So your molecular formula tells you the precise number of atoms of each element in a compound. Your empirical formula tells you the ratio between them, okay? So it looks, sometimes can look a bit different from your molecular formula, but it's mostly used for determining the ratio and kind of showing it in its simplest form, all right? So these questions I've taken directly from some of the exam papers, okay? So I'm on this one here. Okay, so calculate the empirical formula of the tin salt stannous fluoride, a compound added to toothpaste to prevent tooth decay. Its mass percentage composition is 24.5% or 24.25% fluorine, 75.75% stannous. So again, for the step, these, okay, you assume you have 100 grams of whatever you're working with. Okay, so we don't need to know anything in particular about its mass. If it doesn't tell you a mass, you can assume you have 100% or 100 grams, okay, because it makes the percentage to mass conversion much easier. Okay, so I'm going to assume I have, oh, sorry, assume 100 grams of that stannous fluoride. Okay, so your step 2 then is to work out the mass. Okay, work out the mass of each element. Okay. Okay, so we have 2 of these. We have S and we have F. And this is why we assume we have 100 grams, okay? Because it makes this percentage conversion an awful lot easier. So if I know I have 75.75% of 100 grams, that's just going to be 75.75 grams. All right, so if I took 75.75% of 100 grams, it just works out as 75.75 grams. So we don't need to kind of do a lot of conversion using a certain mass, okay? We can just assume we have 100 grams. In the same way then for my fluorine, I have 24.25% of 100 grams, which is just 24.25 grams. Is everyone okay with that so far?
Yes.
Okay. You guys can still see the worksheet, yeah?
Yeah.
Perfect. Okay, just bear with me 2 seconds now. Okay, so your step 3 then is to work out the moles. Okay, so you're going to convert each one of these to their mole amounts. Oh, sorry. Okay, so based on what we covered last week, okay, so you'll use your triangle to work out each one of these, okay? So I don't have it on, or do I? Hold on, sorry. Yeah, I do actually. I'll just put this up here just so we can see it. Of course, it gets in the way of everything. Okay, so this triangle we use typically just to simplify what we have to do to convert mass to moles and moles to mass. So in this case, I'm going to cover what I'm trying to calculate. All right, so I'm trying to calculate mass. Oh no, sorry. I'm trying to calculate moles here. So if I cover that, essentially, it tells me to divide the mass by the molar mass of each of these elements. Okay? So for moles, it's going to be your mass divided by the molar mass. All right, because I'm trying to work out the moles of each one of these elements. I have a mass value. I can take their molar mass directly from the periodic table, and then I can work out the ratio between them. Can everyone see where I'm getting that from? Yeah? Okay. So in this case, then, so for my stannous, I have 75.75 grams, and I'm going to divide that then by the molar mass of that compound. Just bear with me 2 seconds and I'll just have a look on the periodic table. Okay, so that's 118.7 grams per mole. Okay, so I'm going to work that out then. So just divide that mass figure, so 75.75, divided by 118.7. So we should be getting around 0.638 for that. Okay, so I'm going to do the exact same thing for our fluorine there. Sorry, just 2 seconds. Okay, so we have 24.25 grams. And our molar mass, according to our periodic table for fluorine, is 19 grams per mole. Okay, so that's 24.25 divided by our 19 grams per mole, which gives us, we'll say 1.276. Everyone okay with that so far, yeah? Okay, so your step 4 then is to find the ratio between each one of these. Okay? So the kind of rule of thumb here is to divide by the smallest. Okay, so I'm going to highlight each one of these. All right, so this one is kind of simpler to what we've done previously because there's only two. So it's easy to spot which one is the smallest. Okay, so if I want to make a ratio of these two in terms of moles, all right, so it would be 0.638 is to 1.276. So in this case, all right, so my tin or my stannous is 0.638, so obviously that's the smallest. So I'm going to divide each one of those by the smallest mole amount. Okay, so 0.638 divided by itself is 1. And then 1.276 divided by 0.638, it's actually 2. All right, so it nearly rounds up to 2. Okay, so all I did here was simplify this ratio by dividing each one by the smallest small amount. Your last step then, so your step 5. and you just need to write the empirical formula. Okay, so what I recommend doing in the exams is write each one of your elements, just like that. Leave a space in between each one so you can write these numbers as subscripts. Okay, so both of these are going to be subscripts next to the element itself. So just to show you where it comes from, it would be S1 there, okay, but you don't have to include the 1, it's 1:2. So you'd normally not write that 1, and then followed by F2. Okay, so what that should look like then, just without that 1 there, is SF2. And that's your final answer for that one, okay? Is everyone happy enough with that, guys? So you'll see, I know I'm only kind of doing one example of each, but they're the exact same format each time, okay? Particularly for the empirical formula calculations, it's these 5 steps over and over again, okay? So you assume you have 100 grams, the mass, then you work out from the percentage. From the mass, then you convert it into moles based on your triangle here and your periodic table. Find the ratio, and then write it as its correct empirical formula, okay? So there's a couple of examples there, but they're all the exact same way, the same 5 steps. Does anyone have any questions on that, guys?
And we do number 3 of that on that one as well.
Yeah, of course. Actually, I was just looking at that one because that one, it's the only exception to the one I could find where it's a little
Yeah,
bit different because we don't have 80, we have 85 grams in total there. So yeah, absolutely not a problem.
oh, thank you.
Okay, so I'm just on part 3 of that one there. So this was taken directly from one of the exams. Okay, so it's a sample of compound weighing 83.5 grams contains 33.4 grams of sulfur. The rest is oxygen. So what is its empirical formula? So I've kind of made a note here already, but it's a little bit different because you don't assume you have 100 grams. You use the mass that's given in the question. So I'm going to do in the exact same way, but we won't have to do step 1. All right. So we have a total mass of 83.5 grams, okay? And we're told that it's made up of sulfur and we also have oxygen. Okay, so we're told that in the question. So we still only have 2 elements here, okay? We're told that out of that 83.5 grams, 33.4 grams of it is oxygen. So if you're kind of following along with the steps, I've almost skipped ahead to step 2 here because we can't assume we have 100 grams, all right? For oxygen, then, this is a little bit different, okay? Because we weren't told what the mass of oxygen was, but we were told a total, and we were told that 33.4 grams of it is made up by sulfur. So what you do for oxygen is that 83.5 grams is a total. I know 33.4 is made up of sulfur. So taking one from the other should give me my total mass of oxygen. All right. So that would be 83.5 grams. And we're going to take away my mass of my sulfur there. So what I should have for oxygen then is 50.1 grams. So that's where that question differs a little bit, okay? Because we didn't assume we have 100. We were given the total mass, but we had to work out the mass of one of the elements, okay? What they'll normally do is that they'll give you 3 elements, 2 or 3 elements. They'll give you the total. They'll give you the mass of either 1 or 2 of those elements, and then you'll just have to work out the remainder. So you just take them both away. All right. So we'll complete this question, okay? But it's in the exact same format, all right? So you'll see it's almost like practice makes perfect with these, okay? So we're going to convert the moles to mass, or mass to moles, sorry. When you say it so often, you kind of get confused between them the whole time. It's like, I don't even know what I'm converting anymore. So I'm going to take then, there's our triangle down here, so we have it handy. Okay, so in the exact same way, all right, I have two mass values. I'm going to convert each one of these to the moles based on the periodic table. Okay, so my moles there is our mass divided by molar mass. Okay, so if I essentially cover what I'm trying to calculate, so if I cover that, I have my mass value, I'm going to divide it by the molar masses that are in the periodic table. Okay, so my molar mass of sulfur then. Okay, so on my periodic table then, this will be 33.4 grams from the question divided by 32 grams per mole. Okay, so 33.4 divided by 32 should give us a mole here of, we'll just round out 1.044 moles. Can everyone see where I'm getting that from, yeah? Okay, so for our oxygen, then we're going to do the exact same thing. Taking our same equation, mass divided by molar mass. So that will be 50.1 grams. And I'm going to divide that then by 16 grams per mole. Okay, so that should give us, going to 3 decimal places, 3.131 moles. Everyone okay with that, guys? Yeah? Okay, so step 4 then, similar to what we had above, we're just going to work out the ratio. And again, dividing each one by the smallest. All right, so I have sulfur and I have oxygen, okay? Based on what we've just worked out, I have 1.044 moles of sulfur and 3.131 moles of oxygen, all right? Obviously then my sulfur is going to be the smallest mole amount, so I'm going to divide each one of these by the smallest. Okay, so 1.044 divided by itself is going to give me 1. And then 3.131 divided by 1.044. So it gives me 2.999, but you round it up to the nearest whole number. Okay, so that'll give me 3. All right. And then your final step then is just to write that as its empirical formula. All right, so I have sulfur, I have oxygen, and I'm just going to go back in and fill these numbers in as subscripts to represent I have my simplest ratio. Okay, so just showing you there, my 1 will go there, and my 3 will go there. Or for the exam, what I do is I just get rid of that 1. All right, so it'll be SO3. Is that okay, guys? Brilliant stuff. All right. So, guys, what I might do now is just gone 6 o'clock there. Okay, so I know this is kind of fairly heavy in terms of calculations. So what I'll do is I'll give you maybe a 5-10 minute break. I'll come back. I'll do some of the kind of conversion of mass to moles. And then all we'll do tonight then is just introduce the lecture notes rather than kind of go through all of those. Because I think it's important that we get these bases down because these are going to kind of form most of the basis for what we're going to cover tonight anyway. So once we're going to get good practice with these, then we can move on to where these are used for like titrations and things like that. Does that sound okay?
Yeah.
Perfect, guys. All right. So if we say we're back here by about 10 past 6, and when we'll finish some of these questions off then, okay?
Yeah.
Yep, no problem. Cheers.
Again. And then I'll start sharing the screen. Just bear with me 2 seconds. All right, guys. Can you see that okay? Yeah? Okay, perfect. So I'm going to move on then to converting the mass to moles questions, all right? So this is where kind of all of the theory based on what we've done already kind of comes into practice in one big question, I suppose. All right, so I might do maybe 2 or 3 of these and then I'll move on to the lecture notes that we were going to do this evening, but I'll only start covering maybe a couple of slides and then we'll pick it up there next week. Okay, so moving on to this then. So we're given this equation, okay? So B2H6 plus 2 molecules of oxygen is equal to 2 HbO2 and then 2 moles of water. So this asks how many grams of oxygen will be needed to burn 36.1 grams of B2H6. So like I said, with any of these questions, what I recommend you do is work out the molar mass of what you're working with. All right, so that should be your first port of call for any of these questions. So in terms of this, I'm going to need both of these, okay? So the question mentions both oxygen and it also mentions B2H6, okay? So I'm going to work out the molar mass of both of these because I'm going to need it eventually, all right? So I might as well work them out at the start. Okay, so molar mass of, I'll do both of them. So molar mass of oxygen first, all right? So again, oh, sorry. So again, list the element that you have. In this case, is only oxygen. From the periodic table, each atom of oxygen weighs 16 grams per mole. In oxygen gas, I have 2 atoms of oxygen, so I'm going to multiply that by 2. And that will give me 32 grams per mole in total for oxygen. All right? Everyone can see where I got that from, yeah? Perfect, okay. So we'll call it step 1, A and B. I'm just going to work out the molar mass of my B2H6 there as well. Okay, so it's like I said at the start, even if you can't continue with the question, at least you've shown that you can. Sorry, I don't know what's going on there. So at least you've shown that you can work out the molar masses and you've kind of got off to the right start. Okay, so I wouldn't worry about trying to complete the whole question if you can't. If you can get this done, that would be fantastic. Okay, so in terms of my B2H6 there, so I obviously have my boron and I have hydrogen as well. Okay, so just bear with me, I just need to get the boron molar mass. Okay, so boron weighs 10 grams per mole. And we have 2 atoms of boron in B2H6. Okay, so that'll give me 20 grams per mole in total for my boron. Hydrogen then, so has a mass of 1 gram per mole. And based on my molecular formula, I have 6 hydrogen atoms, so that will give me 6 grams per mole. Okay, so to work out my total there, I just need to obviously add those together, which will give me 26 grams per mole for my boron. All right, so there's your step one. Okay, so we've calculated the molar mass. Everyone okay with that so far, yeah? Okay, so moving on from that then. So I'm going to convert the mass of B2H6 that I was given in the question into moles, okay? Because what we do here is we make sure that everything is in moles. So any mass values that we're given, they're converted to moles. And then we use the ratio between them, okay? So that's really important that once we can't just go directly using mass, they always have to be converted into moles first before we can compare. Okay, so I'm going to convert the mass of B2H6 into moles. Okay, spare me 2 seconds now. So again, you'll see me using this triangle an awful lot. Okay, so what I recommend you do on any exam paper that you have is write that somewhere, maybe in the top of the exam paper or just as a note for yourself. So at least you have your step one is done and you also have this then. Okay, so it's almost showing the examiner that even if you can't complete the question, I know what tools I need to use to do it. All right. So in the exact same way that we've done already, okay, so we're looking to convert this into moles. So I have a mass, okay, I've been given a mass value in the question of 36.1 grams there. I've just worked out the molar mass of B2H6 based on my elements in my periodic table. So now I just need to convert it into moles. All right, so I have B2H6. Okay, so if I cover, I'm trying to calculate, just if I'm covering that, it tells me to divide the mass given by the molar mass I've just worked out. So you'll see an awful lot of repetition in these questions. Okay, so in saying that then, so we have 36.1 grams of B2H6 given in the question, and I'm going to divide that then by 26 grams per mole, based on what we've worked out. Okay, so 36.1 divided by 26. So I'm just going to round it up there to 2 decimal places. So you should be getting around 1.39 moles here. Is everyone okay with that, guys? Everyone can see where I'm getting that from. All good?
Yeah. Yeah.
Perfect, okay. Okay, so now I have my mole amount then for my B2H6, okay? But my question specifically asks me how many grams of oxygen. Okay, so I need to kind of look at the ratio between these two reactants here. And by getting that mole amount, I can compare the two and then work backwards by converting the moles back to mass. Okay? So your step three then should be so look at the ratio. And we're going to base this on the balanced chemical equation. Okay, so this is where the kind of balancing chemical equation part comes in. They'll often ask you to balance the chemical equation first, and then you'll have to use it then in your mass to moles conversion. Okay, so I'm just going to copy these down because this is what I'm working with up here. And what I'm looking at here are the coefficients that are in front of my two reagents. Okay, so this tells me the number of molecules that are going to react with one another in this. So the number of moles and the number of molecules. Okay, so we don't need to include a 1 here, but I'm just going to show it to you just to highlight it. Okay, so I took this from the balanced chemical equation, all right? What this tells me is that if I have 1 mole of B2H6, 2 moles of oxygen are going to react with it. Okay, so looking at my balanced chemical equation here, there's a pretend 1 in front of that B2H6. So if I have 1 mole of this, 2 moles of oxygen will react with it. So that's like the ideal ratio or the theoretical ratio. Okay, so if I have 1 mole, 2 moles of that will react. So it's a 1:2. Okay. But I don't have 1 mole. Okay, so what I worked out here is actually 1.39. Okay, so it's not a simple 1:2. I actually used 1.39 moles. So can anyone suggest what I have to do to work out the moles of oxygen? So if I
Divide
should,
by the smallest, isn't it? Yeah.
no, so that will be for your empirical formula. Okay, so this is
Oh,
a little
okay.
bit different. Okay, so what I do here is that my theoretical ratio, or what I should have, is 1:2. All right. This reaction, this was done in a lab, and they actually used 1.39 moles. So what I have to do here is multiply that by 2. Okay, so this would have been simple if we had 1 mole there, because I would have just or used 2 moles of oxygen. But in this case, it's 1.39 moles that were used. So I need to make sure that I multiply that by 2 to get the correct mole amount.
Okay.
So in this case, then it's actually 2.78.
Yeah.
Okay, so I'm just going to put that in brackets, so you multiply by 2.
Yeah.
All right.
Yeah.
Okay, so what that is the moles of oxygen formed. Or moles of oxygen used, I should say, sorry. Is everyone okay with that so far?
Yeah.
Okay, so now I have a mole amount, okay, which is great. But the question asked me to work out how many grams of oxygen, okay?
Yeah.
So I have my moles, all right, so I can tick this off my triangle here. I have a mole amount. At the very start, I worked out that I have 32 grams per mole for oxygen for my molar mass.
Mm-hmm.
So I have everything I need to work out the mass amount. So I'm going to convert it back again, all right? So our step 4 here is going to be convert the moles to mass. Okay, so just to show you then, again, we worked out the molar mass. We have that. We have the mole amount now. So if I cover, just pretend that's covered there, it tells me to multiply the moles that I got by the molar mass. All right. So for my oxygen then, so to work out the mass amount, I have to multiply the moles by the molar mass that I worked out at the start. Okay, so what I have here then is your 2.78. 2.78 moles multiplied by the molar mass we worked out at the very start for oxygen, which is 32 grams per mole. So what I should have here is 2.78 by 32. So that will give me 88.96 grams of oxygen. And that's my final answer for that one. Okay, so what that tells me in the question, so it says how many grams of oxygen will be needed to burn 36.1 grams of B2H6? And we've worked out that it's 88.96 grams or 89 grams will be needed to burn 36.1 grams of our B2H6. Is that okay, guys?
Yeah.
Okay, so I'll do one more of those. Okay, so as you can see, it's just practice makes perfect with these. It's the same formula over and over again. All right. So I'm going to do this one here. Okay, so the part 4, which is aspirin is synthesized using the esterification reaction. Okay, so it does, like I said, it gives you a little bit of a spiel about the reaction or the compound itself. Okay, so what this tells me is that the balanced chemical equation is this. It's outlined the SOP to 25 grams of salicylic acid. Okay, so that's an important thing, so I'll highlight that. how many moles of aspirin can be theoretically be produced from this reaction. Okay, so this is the exact same thing again. It's just asking us in a different way. All right, but it's again the exact same layout. Okay, so I'm going to start out with step 1. And I'm going to do step 1A, okay? So I'll work out the molar mass of what I've been given in the question, okay? So this is salicylic acid in this case. All right, so salicylic acid has, and based on its molecular formula here, all right, so it has a carbon, it has hydrogen, and it has oxygen. Okay, so as we have before, 12 grams per mole for our carbon, multiplied by our 9 carbon atoms. Okay, so, or sorry, 7 carbon atoms there. Okay, so this one here, C7H6O3. I have 7 carbon atoms there. So that will give me 84 grams grams per mole in total for my carbon. Hydrogen then is our 1 gram per mole multiplied by my 6 hydrogen atoms, obviously to give me 6 grams per mole. And then our oxygen then is 16 grams per mole multiplied by 3 oxygen atoms. And that will give me 48 grams per mole in total. All right, so just to get the molar mass, then you add each one of those up, which what we should be getting here is 138 grams per mole. All right, so the very same as what we've had before. Okay, so moving on to step 2 then. So we're given a mass of salicylic acid in the question. Okay, it's that 25 grams there. So looking at what we have in our triangle to take off, we're given a mass. We've worked out the molar mass of what we have. We need to convert that to moles, and I have each of the values I need to do that. Okay, so as per usual, step 2 is to convert the mass to moles. Okay, so for this, again, the moles is your mass divided by your molar mass. Okay, so we've just worked out what we're given the mass, sorry, in the question, so 25.0 grams. And we've worked out the molar mass as 138 grams per mole. Okay, so just dividing that mass then of 25 divided by 138. So what we should be getting here is something around 0.181 moles. Is that okay, guys? Everyone can see where I'm getting that from, yeah? All right then, so we now have a mole amount, okay? So now I need to look at my ratio between what I was given and what I need. All right, so in this case, I worked out my salicylic acid moles, but I need to look at how many moles of aspirin that will form. Okay, so I'm going to just copy this balanced chemical equation down here so we can see it. And 99% of the time, they will tell you which one is which. Okay, so you can see it there. So I'll scroll back down. So your C7H6O3, they'll tell you that's salicylic acid in the question, and then aspirin then is C9H8O4, and that's in their balanced chemical equation. Okay, so they will tell you more often than not which one is which. So looking at our ratio then between our salicylic acid and our aspirin, which is C9HAO4. Okay, so can anyone tell me what the ratio is between both of those based on their coefficients? So looking at the balanced chemical equation itself. Okay, so just looking at these two in particular. Okay, because they have no coefficients there, it's a 1:1 reaction. Okay, so I know that if 1 mole of salicylic acid is used, so we don't include the 1 there, but if I use 1 mole of salicylic acid, it will form 1 mole of my aspirin. Okay, so the ones just aren't visible there, but it's a 1:1. And we'll call this is our theoretical ratio. Okay, so if I used exactly 1 mole of salicylic acid, it will form exactly 1 mole of our aspirin. Okay, when saying that though, I didn't use 1 mole. Okay, I used 0.181 moles of salicylic acid. Okay, so we worked that out. Salicylic acid, we've used 0.181 moles. So can anyone tell me how many moles of aspirin I should form then, based on that?
And 181 as well.
Yeah, exactly. Okay, because it's a 1:1 reaction. Okay, so whatever I use of my salicylic acid, I will form the exact same number of moles as my aspirin. All right. So again, if we had used exactly what we needed, it would have been 1 mole to 1 mole. We used less than what we needed, which is 0.181, but it will still react to form 0.181 moles of aspirin. Okay, and that actually answered that question for us there. Okay, because it says how many moles of aspirin can theoretically be produced in this reaction. So we've answered that question. Okay, so that is your final answer of 0.181 moles. So what I'd recommend you do, I'll just call that. So when you look at the balanced chemical equation, so the first ratio I have, that's called your theoretical mole ratio, okay? And that's always taken from your balanced chemical equation. Whereas we'll call this one here the actual mole ratio. And that's taken from your figures or your values. All right, so what you should be looking to do here is compare one to the other. All right. So I won't do step 4 here because I didn't ask to convert it back to mass, but it will be done in the exact same way as you would have done in the previous example, okay? Is everyone okay with that, guys? Does anyone have any questions before I move on? All good? Okay, perfect. So what I'll do is I will stop sharing the screen and I will just start on the first couple of bits then for our lecture this evening. But I won't do too much because I know the calculations are quite heavy, so we'll just get started on this and we can go from there. Can everyone see that okay? Everyone can see lecture 5?
Yeah.
Yeah.
Okay, perfect. So we're looking at our yield calculations and then we're moving into some of how we use the moles to work out concentration in solution. Okay, so we're taking the moles calculations that we've just done and taking it a little bit further into how we work out the concentration of some solutions. All right. So can you guys see the theoretical yield slide? Yeah. You can see the
Yeah.
slide?
Yes.
Yeah.
Perfect. Okay. So for some of those moles calculations, okay, they'll often ask a question based on theoretical yield. Okay. So it's basically taking what we've done so far and adding a little additional step to it and working out what's the maximum amount of product that can be formed from a chemical reaction. Okay, so it almost tests reaction efficiency or how much, if this reaction went 100% perfectly and everything went well, there was no loss, how much product would actually form at the end. So it's called the theoretical yield. Okay, so it's the maximum amount of product that can be made from a chemical reaction. So in other words, it's the amount of product possible as calculated from the balanced chemical equation. So very similar to what we've just done this evening, looking at the ratios between our reactants and our products, and the mass of what's called the limiting reagent. We're not going to delve too much into limiting reagent calculations, okay, because we don't have to cover it, but most of the exam questions will tell you what the limiting reagent is. What I'm going to do is just introduce what it is, and it's basically the reactant that runs out first. So often in a chemical reaction, what you'll have are two or more reagents. One will always run out first. Okay, so it will run out, it will be used up in the reaction, and that's when the reaction stops. The other reagents are what's known as being in excess. Okay, so we often have too much of those. The limit reagent decides how much of that product will form. Once that has been reached and once that's been used up, the reaction will stop. Okay, so no more will form. It's kind of like the analogy with, do you know, like the boxes of brownies you can make? So if you had, say, one box of brownies and that would use up 2 eggs per brownie pack. We have one box and we have 2 eggs, but you've bought a carton of 6 eggs. You can only make one box of brownies based on 2 eggs, but you'll have 4 eggs to spare. So they'll be in excess. Okay, so it's the very same theory behind it. One of the reactants will always run out first and it will determine how much you use or make at the end. So I'll show you this, okay, just as a quick example. That if I were to show you the production of water, all right? So what this tells me is that 2 moles of hydrogen will combine with 1 mole of oxygen, okay, so that invisible 1 coefficient there, and that will form 2 moles of water, okay? So 2 is to 1 is to 2. If I looked at the mole ratio between just my reagents here, okay, so just on the left-hand side, it tells me it's a 2 is to 1. Okay, so 2 moles of hydrogen, 2 moles of my oxygen there. Can everyone see where I'm getting that from? Yeah? Okay, so 2 moles of hydrogen to 1 mole of my oxygen. So if I were to do this reaction and I went into a lab and I used up 4 moles of hydrogen and I only used 0.5 moles of oxygen, the new ratio wouldn't be 2 is to 1 anymore. It would be 4 to 0.5. Or if I simplify that a little bit further, it's 8 is to 1. So can everyone see there that, like, no matter what I do, 2 moles of hydrogen will always react with 1 mole of oxygen to form 2 moles of water? If I did this experiment and I used 4 moles of hydrogen and 0.5 moles of oxygen, I now have oxygen in as a limiting reagent. Okay, so I only need 2 is to 1. I've added hydrogen in much more excess than what I need. It will only ever form this way. So oxygen will determine how much water I will form rather than hydrogen. Okay, so we have far more hydrogen than what we need in that reaction. Okay, so that's where we get that from. I won't go too much into how we calculate that because it is a lot of mole calculations that we don't necessarily need to cover. But it's just to show you that one of the reactants will always determine how much of the product is made. Okay. So this is where it actually comes from then. Okay, so you can find the percentage yield of a product, so determining basically reaction efficiency by comparing the amount that you obtained through experiment to the maximum amount that possibly could have been made. So that's your theoretical yield. Okay, so we look at the reaction, we say, okay, so if at max 2 moles of product would form and that equates to 50 grams of product, but I come along and do that same reaction and I only get 30 grams of product, I'm only operating at 60% percentage yield, which means something went wrong during that reaction. Okay, so we lost an awful lot more product than what we made, and our yield isn't good. Okay, so again, if you're looking at the pharmaceutical industry, that can occur additional costs. You're losing too much product, you're not operating at a certain efficiency, and therefore you need to look at how the reaction is actually progressing. Okay, so that's where it kind of ties into the real world a little bit. So for example, okay, oh, sorry. So that example from slide 2, okay, so based on what we just covered, oxygen is our limiting reagent there. So oxygen will always determine how much water is formed. Because hydrogen is in excess, it won't do it. So looking at this, and I'll just go back here, we use 0.5 moles of oxygen. Okay. Okay, so I use 0.5 moles of oxygen rather than the 1 mole I needed. Okay. From the balanced chemical equation, the ratio between oxygen and H2O is 1:2. Okay, so if I look at oxygen, that's my reactant that's going to determine how much water is made. What I should have used here is 1:2, but I used 0.5. So similar to what we've just had, okay, if the reaction is 1:2, I use 0.5 moles. I need to multiply 0.5 by 2 to get the most amount of product that is going to form. And that's going to be 1 mole of water based on that, okay? So it's 1:2 reaction. I use 0.5. I multiply that by 2 to find out, well, how much product can I make? And from what I use, I can only make 1 mole of water at most. Okay, nothing else is going to form because oxygen is going to run out. Then through kind of converting the moles to mass, similar to what we've just done in some of our examples there, converting moles to grams using the molar mass of water. So if I form 1 mole, the molar mass of water is 18 grams per mole. So if I multiply 1 by 18, similar to what we've done already, I can only form, I can only form 18 grams of water at most. Okay, just converting the moles into grams there. So say, for example, if I completed the reaction and I only formed 15 grams of water. So, sorry guys, I don't know why that's jumping back. So I can form at most 18 grams. I completed the reaction and only formed 15 grams of water. My percentage yield would be my actual or my experimental yield, which is 15 grams, divided by my 18 or my theoretical yield, and multiplied by 100. Okay. So if I were to look at the efficiency of that reaction or the yield of that reaction, it would only be 83% rather than 100%. So what that would tell me is that if I were to look at the reaction and go back, what could I more carefully control the next time? So I can push the efficiency further, or I can get to that 100% of my yield. Okay. So in terms of water and in certain gases that I've used, some gases might have escaped into the lab. The lab might have been too hot, some of the water might have evaporated, and it decreased my percentage yield. Okay. So we always compare this figure to what we should have gotten. All right. So if it's close to 100%, like no reaction is ever going to 100%. But if it's as close as possible to 100%, it's considered satisfactory or it's a suitable reaction. If it's below, and this one is okay, but if it's very low, maybe below 70%, it indicates that something has gone wrong and you've lost an awful lot of product during the reaction. Okay, so this will become more apparent when we're doing the lab work, but I just wanted to introduce it to you so you know to kind of keep an eye out for percentage yields and what they actually mean. Okay. Is everyone okay with that, guys? So what I might do just at the start of, because I know this is kind of another calculation in on top of it, but once we start next week's lecture, I'll go back and I'll do a couple of these examples out, and then you can see where that's actually coming from. I just wanted to introduce it to you tonight, and then we'll start next week's lecture with a couple of examples of these, and then we'll keep going with the lecture if that's okay. Does that sound all right? Okay, perfect.
Yep.
So guys, I might leave it there for you this evening then, because I think I've melted your head enough with calculations.